Okay, good evening, everybody. Let me first turn on the recording. Recording cloud. Yep. Okay, so we have progressed on the theory quite a bit far, and we are already on the module 9, no, module 8. Module 8. So this is all about, we started with a pipeline to improve the processor performance uh, with parallelism, and we'll now explore different other parallel structures and parallel architecture for the processors in this module, module 8, and that will conclude the processor design part. And in the module 9, we'll be starting with the memory design, especially focusing on the cache memories and the virtual memories to further improve the performance, especially with respect to the cache memory, how it helps in improving the performance of software program for a given processor architecture. And the virtual memory part is basically explain the techniques using which a processor or a programmer on a software program enjoys a vast amount of memory available to it, or at least presented to it, though the real hardware resource on the board is limited. So that's the virtual memory discussion we'll be doing. Uh, so that's the module 9, but module 8 part, this part, we'll be doing this theoretical discussion of different style of parallelization and what are the overall bird's eye view of this whole field, because this is a very open space, and some, if you look at the slides, go through the slides, there are only a couple of generic examples are given, like overall like strategy structure, like that. Exact architectures are secrets of the processor companies. Like Intel definitely don't want to reveal their internals unless it of course helps in their business. You will see in the Intel spec or AMD spec in a very top level view of what are there, what are the components and stuff like that. No, but none of them actually discuss detail about what's internally there, how it is implemented, except for one processor, which is not uh, nowadays not much significant in the market, but once it was really huge, which is the Spark processor from Sun Microsystem. I'm not sure if you guys have heard of that, or at least some of you have heard of the Sun Microsystem, and how it helped like .com boom during that 2090s 2000s era. Um, they have this open Spark documentation, and it has all the nitty-gritty details about that processor, and you can actually study. It's very interesting to study, out of our scope in this course, but if you are interested, you can actually explore that and see how an industry level parallel processor are architected and implemented in very, very detailed level. But as far as the class discussion goes, it's more like a very superficial discussion about top level ideas like multi-cores, SMPs, bus-based system, and so on and so forth. Um, that's one thing. Any question on these or anything else? You can ask me any question. Okay, no question from audience. So this specific topic, you will be seeing something called hardware trading. So let me make it make so very clear this concept. Let me try to make that hardware trading. So I'm talking about these slides, basically hardware trading and all the related component concept and how the hardware trading works in the Spark T1 core data path. Um, but this one, just don't mix up with the software threads. I know many of you have actually uh, gone through the parallel programming. If you have not, I would suggest you to take that course. That very relevant in contemporary market, parallel programming and parallel systems. You'll be dealing with threads and multiprocessing, multiprocess communication, and so on and so forth. But these threads, what will be learned in that software field, is basically created, managed by operating system. Maybe in the operating system class, you have come across the thread concept as well. But hardware thread is different than that. Hardware thread is purely, it's to target the distribute the load at instruction and machine level, basically. It's nothing to do with the software program. Software does not control the threads. It's purely based on controller inside the hardware. It creates the threads, distribute the instructions in the thread so that they can manage and optimize their balance, throughput balance dynamically in the hardware. So that concept is hardware threading is different than software thread, and in fact hardware threads are called strands. They are not called thread in the hardware world, they call us strands. So that's the one part I want to make sure that you take a note and say that they are different. It's different than software threads. Question? I don't have much topic to discuss tonight. So, yeah, I'm just hoping to get questions from you. Uh, may not be on this topic, maybe other topics, maybe on your project. You're all welcome. No, how is the project going on? Project 3, have you guys started? Some said. One question: when the project to be posted? We are grading, under grading process. Let's see. There are, yeah. First, grader will grade them. Then I need to do the logistics, and maybe I'll sample some of the checkings, gradings. Uh, let's take in another 2 weeks, maybe, uh, as soon as possible. But let's say max at 2 weeks from now. Yeah, please start. If you haven't started on project 3, please start it. Like it's all the labs basically after midterm. All the labs is that's what we are looking at, and each lab gives you the task. So they are treat them as a milestone, make them done. Okay. One more thing, like I hope you have. Let me see. Uh, I hope you have visited the very front page of our Canvas structure. And how many of you got chance to look at these videos? You see, like I have some reference videos. They're very interesting to look at. I, anyone has watched them? I'm just trying to follow through the chat, but guys, like if you can speak up, please do so. Otherwise, I probably won't be able to keep track with the chats. Yeah, so maybe like right now you basically are ready to actually watch. This is the interesting one, Santo Silicon. Like this one talks about how the hardware chip are made, all the little transistors and wiring between them, and they're packed millions of devices on a 1 millimeter square area. How they're done, it's basically explained here, and you'll be familiar with that process. Very interesting to see. It's all start from the sand or silicon, and then from there how the processor is actually assembled together. This is till the chip, and then make the chip. This part is like how the motherboards are fabricated, like putting all the individual component to make a computer system. And assembling computer is more like, and now we are assembling, taking the motherboards and other components and assembling a computer. And the other part is, this is very interesting. Like I try to share some of the big companies data center, cloud data centers, and those stuff. And what is this technologies? These are all like rows and rows of machines, and rows, like each machines had probably 50s to 100 processor in it, and other hardware components, and they're managing it for like millions of people accessing these machines on daily basis. So these are amazing technology to look at and watch upon, and I hope at some point of time you will be landing in working in this area. At least if you are interested to start working for these companies with the big data centers and stuff like that. That's one way to go. But these are all interesting videos. Like these are optional, but I would highly encourage you to actually watch them once you have time. Okay. Um, all right.
Professor, can you real
Yes.
briefly go over the difference between scalar and superscalar? I know in your videos and your notes you said that
Mhm.
superscalar uses multiple pipelines in parallel, and then scalar just uses one, right?
So scalar uses one, superscalar uses multiple. So if you see like there is a pipeline and super pipeline. We are still talking about this one pipeline resource, okay, and but they are basically running in the double speed than rest of the system. So that's what the super pipeline is, but there is no multiple pipeline involved. But for the super scalar, even like super pipeline, it is more faster, and we can actually scale it as we need, or at least like theoretically. But it involves like multiple pipelines. So that's the super scalar strategy, where we deploy parallel pipelines and inject independent instruction through the pipeline. So uh, for the multi-program environment, this may be very significant, because let's say there is multiple user running multiple different programs. They are not depending on each other, so their instructions are pretty much independent. So let's say there are like 5 such independent program, and for each of this program, one dedicated pipeline is given. So throughput is really big there. Even for the one single program, if you want to speed up, like then we can actually, system can inject independent instruction, data independent instruction through the pipeline. Depending on the what complexity the processor could offer, it might happen that this pipeline, in between them, they don't have data forwarding. So that means data hazard can be an issue if this structure is used on a single program. But again, this is open space, right? So some hardware can decide, okay, I will uh, uh, provide some data forwarding from one pipeline across the pipelines. That can happen too. In that case, it will help the single program a little bit more, a little bit better. Uh, so what else?
Like, when would we ever want to use a scalar like a single pipeline? Because I know in operating systems, whenever we wanted to communicate between parent processes and child processes, we would always use multiple pipelines. So that would be a superscalar program. Whereas, why would I
Uh,
actually want
uh,
to use one pipeline?
you now I got your point. You are actually mixing up software pipeline with the hardware pipeline. So this is real the pipeline which involves your register file, ALU, data memory, etc. The
Yeah,
one you are talking about, the pipeline that you create for the interprocess communication at the software level, they are all created by operating system, and your original hardware may be a scalar processor itself, like may not even need to have a pipeline uh, there. Like it is just a software concept of the pipeline. So that pipeline is different to this pipeline. This is completely hardware level. Am I clear, Akash? Or
yeah, I kind of get it, but at the end, aren't they use like doing this similar tasks? Like the hardware pipeline is communicating between what you said was register files and your ALU, whereas in software, your pipeline would be communicating between different processes.
concept wise, yes, similar. But like at the operating system or software level, you can create as much as pipeline as you need. But at the hardware, it is pre-implemented. Like if a processor has 5 pipeline, that's it. You cannot go beyond that.
Oh, gotcha. I'm assuming most modern day processors are superscalar, right? They have multiple pipelines.
No, not really. May not be. It depends on which processor you are talking of.
Like if we were just talking about like for modern,
So most of the cases, you will see multi-core system is much common in at least in the common systems, because like having like at this level instruction level parallelism with multiple pipeline is actually very specific area of design. It's not that generic processors may have this kind of multiple pipeline involved. Usually multi-core system is much better in the common desktop computing and laptop computing system. It provides like similar facility, but it is more like packing up like 4 processor together in one silicon. So there may not be a pipeline itself, and one register file access pipelines are accessed by uh, one register file in the system. In that case, each core has has different register files, and each pipeline enjoys that register file together. So that makes much more sense to having in the modern laptop and modern systems.
okay, that makes sense. Thank you.
All right. Uh, Anything else you guys want to chat about, discuss about? I may miss any chat point. Let me see.
Who do you think's gonna win?
What's that?
Who do you think's gonna win?
Ah, I don't know. I don't know. So, what's the videos, etc., etc. Nothing much on the chat side. I see. Okay, then what we can do, we can just close to this class discussion session early, way early, and just go and complete your projects. Basically, start working on if you have not started already. All right, then. Good night, everybody, and see you on Wednesday.